In this video, we're going to do the dot product because it's awesome. We're going to do the dot product because there's actually some really nice applications with the dot product. So we're going to define the dot product as the multiplication of each component added together. So if I have this vector u and this vector v, I'm going to multiply the u1 and v1. I'm going to add it to the u2, v2, and etc. And so this is my dot product. Sometimes it's called the inner product. We're going to call it the dot product because we're not working with complex numbers. So if I'm asked to find the dot product of these two vectors, then I'm going to multiply the 4 and the 0. So u dot v is going to give me 4 multiplied by 0 plus the 5 multiplied by the negative 2. So 5, negative 2 plus, then the negative 6 and the negative 3. So negative 6 multiplied by negative 3. So that gives me 0 plus negative 10 plus 18. So my answer is 8. Now notice my dot product produces a scalar. Now, for the next example, I am still going to do it component by component. So I have this 1 and this negative 1. So u dot v is going to be the 1 multiplied by negative 1, the negative 1 multiplied by 2, so plus negative 1 multiplied by 2, and then, of course, the 1 multiplied by negative 4. So 1 multiplied by negative 4. And so we have negative 1 plus negative 2 gives me negative 3, plus negative 4 gives me negative 7. Here's some properties that we get with a dot product. We have the commutative property, the distributive property, the associative property, and the property of magnitude. So if I do the dot product of the vector and itself, I end up with a magnitude squared. So in other words, I don't have to worry about the square root part if I have it on itself. This allows us, these dot products allows us to find the angle between two vectors. And so we say the dot product of u dot v is equal to the magnitude of u multiplied by the magnitude of v, which are both scalars, multiplied by the cosine of the angle between them. And then that gives us that the angle that we are searching for will be the cosine inverse of the dot product divided by each magnitude. The angle that we are looking for will be between 0 and 180 or 0 and pi every single time. Our choices is that it can be an acute angle, such as this. It can be an obtuse angle. It can, of course, be a straight line, and it can also be a 90 or pi over 2. In particular, when we have an angle that is pi over 2, we say that they are orthogonal. The vectors are orthogonal. So we want to find the angle in radians between these two vectors. Go to 2 decimal places. So we know that the angle theta is equal to the cosine inverse of the dot product a dotted with b divided by each one of these magnitudes. So the first thing I'm going to do is I'm going to find my dot product a dotted with b, not a dotted with a dot with b. So I'm going to do 3 times the 1 plus the negative 1 multiplied by the negative 1 plus the 2 multiplied by the negative 2. So my dot product is going to be 3 minus becomes plus and then minus 4. Oh, this is 0. That's nice. The reason that's nice is because I know that the magnitudes of each one of these are not 0, but I do know that I'm going to have the theta is equal to the cosine inverse of 0. So no matter what I'm dividing into 0 by, it's going to be 0. So that tells me that these are orthogonal because the angle between them is pi over 2 or 90 degrees. So that was kind of nice. Let's take a look at the next example. Of course, I have to find my dot product, a dotted with b. And so to be 1 multiplied by 1 plus the negative 2 multiplied by the 1 plus the 1 multiplied by the negative 2. This gives me 1 minus 2 more, which gives me a negative 3. I'm going to then find my magnitude of a, which is going to be the square root of 1 squared plus negative 2 squared plus 1 squared. So this is going to give me the square root of 6. I'm going to find the magnitude of b, and so this is going to be 1 squared plus 1 squared plus 2 squared, which is 4. so the square root of 6. So then my theta is equal to the cosine inverse of negative 3 divided by 1 plus, so I have the square root of 6 multiplied by the square root of 6. So in other words, I have the cosine inverse. So theta is equal to the cosine inverse of negative 3 divided by 6, which gives me the cosine inverse of negative 1/2. That's kind of nice because that's on the unit circle. That tells me that my theta is going to be equal to, it's a 30 in quadrant, it's a 60 in quadrant number 2, which gives me 2 pi divided by 3. So that is my angle between them. Let's take a look at this one. We're asked for the normal or orthogonal vector to this given plane. So the first thing I'm going to do is I'm going to rewrite this equation. So I'm going to rewrite this as z minus 4 x minus 6 is equal to 7, 5 minus 1. I'm going to go ahead and distribute the 4. So I've got z minus 4x plus 24 is equal to 35 minus 7y. Now I'm going to rewrite it so that I have it in the x, y, z on one side and the constant on the other. So negative 4x plus 7y plus z is equal to, and I have 35 minus 24, that gives me 11. So I have this plane that will go through these points. The vector that is going to be normal to this is negative 4, 7, and 1. And I would encourage you to go to GeoAlgebra and graph this to confirm. We're going to talk more in depth in this when we get into the next couple of sections, but this is just kind of give you a teaser of what's coming on. We also, with our vectors, have something called directional angles. It is the angle that is made with each one of the coordinate axes. So we see that the alpha goes with the x, the beta goes with a y, and the gamma goes with a c. So I'm just kind of zoom in. Here's my vector v. And with my vector v, I have this angle that is off, whatever the angle is, off of the x-axis, the angle off of the y-axis, and the angle off of the z-axis. So if we're asked to find each one of these directional angles, it's a lot of work, but it's not difficult work. It's just a lot of work. So we're going to start out with our alpha. So we're going to do the cosine of alpha. This is with respect to the x-axis. This is going to be equal to my u vector crossed with my vector, my unit vector in the x direction. So it's going to be crossed with 1, 0, and 0. And that's because I'm going along the x-axis. So I want to use the unit vector in the x-axis. And then it's going to be the square root of, well, actually, I'll do it with a magnitude. And in fact, I'm going to call I is equal to 1, 0, and 0, because that's in the I direction. So I'm going to just notationally change my mind. It's going to be u dotted with I. These are vectors, the u and the I. All right. So when I do this this dot product in the numerator, I'm going to end up with 2. And the dot product in the denominator is going to, or the magnitude of u is going to be 4 plus 4 plus 1, square root of 9. And the other one is going to be the square root of 1 because it'll be 1 plus 0 plus 0. So I end up with 2 over 3. So my alpha is going to be the cosine inverse of 2 over 3. And we want to go to degrees on this one. So I end up with, in degrees, 48 degrees. So that's my alpha. J is going to be the 0, 1, 0, 1, 0. There we go. So the cosine of beta, which is in the y direction off of the y-axis, is going to be equal to my u dotted with a j, and then the magnitude of u multiplied by the magnitude of j. So the u and the j, the magnitudes, the u magnitude is not going to change for when it was before, and the j magnitude is going to be like the I magnitude because it's in that direction. So the cosine of beta, and I used theta because I like beta. I like theta too. It's all really nice. is going to be, my dot product in the numerator is going to be 2, because it's going to be 0 multiplied by 2, 1 multiplied by 2, and 1 multiplied by 0. Square root of 9, square root of 1. So I get 2 over 9. Square root of 9, that is. So I get 2 over 3, which is going to be the same thing as we had before. So beta is going to be the cosine inverse of 2 divided by 3. So beta is also 48 degrees. I'm going to do my last one, which is my gamma. So I have the cosine of gamma. My k is going to be 0, 0, and 1. So this is going to be u dotted with my k. My magnitude of u, still the square root of 9. Magnitude of k is still going to be 1. So the cosine of gamma is going to be equal to, in this case, I have just 1 in the numerator. And in the denominator, square root of 9, square root of 1, which is 1/3. So gamma is equal to the cosine inverse of 1/3. So I put that in my calculator and I get 71 degrees. All right, so I found the angles. So my directional, so these are all my angles. So let me say this is part of the answer. These are all my angles rounded to the nearest integer. The directional cosines would be the cosine of alpha is equal to 2/3. So that's the other part. Then I have my directional, my directional cosine is going to be the cosine of beta is equal to 2/3. So that's the other answer that we're looking for. And then, of course, this is going to be the cosine of gamma is going to be 1/3. So that is my other answer. So I'm going to go ahead and let you do this one. Not much different, except for it's 1, -2, and 2. So I want you to go ahead and try this. So put this on pause, try this yourself, and I will give you the answers. Welcome back. So the cosine of alpha for this one, you should have got 1/3, which gives me an alpha of equaling 71 degrees. Should have gotten a cosine of beta to equal -2/3, which gives me a beta equal to 131.8 degrees. And then my last one, which is the cosine of gamma, is going to be equal to 2/3. Sure like 2/3. And then that means the gamma is still going to be 48 degrees. And so those are those answers. Go ahead and take a look at yours. And of course, we will talk about them in class if you'd like. If there was anything in there, I know I went fast. So if there's anything in there you want to go over in class, just bring that up in class. All right, projections. Boom, 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 projections. What projections allow us to do is to break down the vectors into its components. And you want to think about this as what would, if you were to take the vector v and shine a light right here, shine this lovely light, how much of this would be shaded? How much of this, if you project that v onto u, how much would be actually shaded on the u part? So the projection of v onto u is noted as this v onto u. The subscript is what it's being projected onto. And it's going to be equal to the dot product of u and v divided by the magnitude of u squared. These are all scalars, and then it gets multiplied by the u vector. So let's go ahead and find, and the scalar projection is going to be the magnitude of the projection of v onto u. And that is the scalar projection, or it's denoted as COMP of v onto u. Okay, so let's take a look at this example. And then we're going to see why we learn this stuff, because we're going to have some real applications here. So our first thing is, what does this look like? Well, if I were to draw these vectors, I'm going to have something that looks like this. I have my u vector. It'd be much better if I did this in GeoAlgebra, because, way better. But I have some u that's going to look like this. And I'm going to have some v that's going to look like this. And I want to know what this is when I project it down on there. And that is going to produce a 90-degree angle. So what we need to do is we do the projection of V onto U is going to be equal to the U crossed with V divided by the magnitude of U squared. And then we multiply that by the vector U. So my cross product, or the dot product, excuse me, the dot product of these two is going to give me 16. 4 times 0, 4 times 4 is 16, 0 times 1 gives me the 16. Now, this magnitude is going to be the square root of, but then it gets squared. So in other words, it's just going to be the 16 plus 16, which is 32. So this is 32. Now my U is 4, 4, and 0. And so what I end up with, because I have 16 over 32, which is 1/2. So this is 1/2. And then 4 and 4 and 0. This ends up becoming 2, 2, and 0. So basically what projections do is it scales down the my U vector. This was my U and this was my V. It kind of, what it does is scales. It could scale up though. So I don't want to say it scales it down always. It could scale it up too. Now, then the scalar projection then is going to be the magnitude of the projection I just found. So then my comp U of V is going to be the magnitude of 2 squared plus 2 squared plus 0 squared. And this is going to give me 2 root 2. So there's my two answers. Kind of cool. Not bad. It's really not bad. What we're doing right now could be considerably worse. You know, we could go back to chapter 6. So this isn't that bad. I don't think it's that bad. The only reason we do all this is so we can do work. So how do we define work? Work is the force. Here's my force. Work is done from point P to Q as the force acting at an angle that is in line with the motion given. So here's an example. A parent is pulling their child on a sled with an angle of 20 degrees with a horizon, with a force of 25 pounds. Now, pounds tells me here that it is already the force, and I don't have to worry about multiplying by gravity because it's in pounds. Not a mass, this is in pounds. They pull the sled in a straight path of 50 feet. How much work was done by the parent pulling the sled? So all we have to do then is find the work, which is equal to the force. The force is 25 pounds. And then I have to do the distance I need to travel. I need to travel 50 feet, excuse me. That is the magnitude in that direction, so 50 feet. And then the cosine of the angle, which is 20. So my answer is about approximately 1175 pound-foot. That's it. Not too bad. Like I said, this stuff isn't that bad. Now, let's take a look at my last example. We have this vector P. Represents the price of a certain model of bicycles sold by the bicycle shop with the vector N. Represents the number of bicycles sold of each model respectively. Compute the dot product and explain what it means. So just going to do the regular dot product. And when I do my P dotted with N, I'm going to end up with 150 multiplied by 10 plus 225 multiplied by 7 and plus 375 multiplied by 9. My final answer is 6450. What does this represent? This represents the total amount of money selling the bicycles at those values. So that is the total amount of money selling those bicycles. That's what it means. And that's it. That's it for this section. Not a bad section.